commence. Let's go. Okay. Hello everybody. Thank you to be here for this workshop today. We'll try to present you our project for dismantling reactors. So the idea is to show you how we manage such a quite complicated dismantling, and the study case will be for the reactor of Brennilis in France, Britannia. So first of all, I will introduce myself. So I'm Soulaimane from Graphitech. Graphitech it's a subsidiary of EDF group, dedicated on the dismantling of graphite reactors. In fact, of reactors from first generation, such as graphite geyser reactor or Brennilis, for example. I'll let Juan present himself.
Thank you, Soulaimane. So I'm Juan Miguel Alvarez. I work for EDF DPUD. DPUD stands for the division dedicated for decommissioning and waste management for EDF in France. We are based in Lyon, and we have different missions inside the group EDF. The first one is ensuring the decommissioning of shutdown reactors in France, preparing the decommissioning of future reactors, developing solutions for waste management, and also promote our knowledge, know-how internationally. And for all those missions, to fulfill all those missions, we work hand in hand with our subsidiaries such as Cyclife and Graphitech. So let's take a look at the agenda of this presentation. We will be covering 4 main topics. The first one, we're gonna, before going deeper in the technical solution, I'm going to present the background and where we are developing this robot. Then I'm going to present you some of the feasibility studies that we have done until now to come to this solution. And then Soulaimane is going to present you more in detail the design and the implementation of the solution, and we will finish with some conclusions and lessons learned so far in this project. So before going deeper in the technical solution, I would like to present what is Brennilis, where is it located, and why are we doing this right now. So Brennilis is hard water gas-cooled reactor. Is located in Brennilis in the west of France. Is the only reactor of that kind of technology that we have in France. And it was constructed, the construction started in 1962. It operated during 18 years until the shutdown that occurred in 1992. And from that moment, it started the decommissioning that has happened in different stages. The first one, it aimed to dismantle all the conventional facilities. As you can see here, all the administrative buildings have been demolished and decommissioned. And a second stage where we dismantle some nuclear facilities, auxiliary nuclear facilities, but also big components, large components inside the reactor building. And in 2023, the French nuclear authority granted the license to continue the dismantling, the complete dismantling of the nuclear building. And it will comprehend the dismantling of the core. The particularity of this reactor, the difference with the PWR is that this reactor is horizontal. So it was an advantage at the time during the exploitation of the reactor, because we could charge the fuel from one side and recover the spent fuel from the other one, so we didn't have to stop the reactor for recharging. But it also represents many challenges for dismantling, as we are going to see in the presentation. This final stage comprehends the dismantling of the core, but also all the tubes, the peripheral piping that it's surrounding the reactor. So I'm gonna talk about the different stages that we have in the scenario for dismantling the core. The core, we are gonna start dismantling the carbonic dioxide tubes that send the gas to the reactor to cool it, and also to recover the heat and go to the exchangers. So this is the first stage to dismantle these tubes, and then we will have access to the front of the reactor. Here we are gonna dismantle the fuel channels, extensions that allow to connect the reactor, the vessel, to the charge phases. And once that we have this corridor free, the operation that we are gonna talk in this presentation is this one: is the extraction of the fuel channels, the tubes that allow to locate the fuel inside the vessel. Then we will continue dismantling all the vessel and the top part, the bottom, and all the screens and shields that are around the vessel. So as you can imagine, the radiological environment here is really difficult for any humankind operation. At the center of the reactor, the estimated dose rate is about 2 sieverts per hour, and here where the robots are going to work, we estimate it at 700 millisieverts per hour. So we cannot go with operators for doing this kind of operations, and that's why we intended to use robotics for this. A little bit more about the extraction of the tubes, because it's also very difficult. You imagine here that we are going to cut every tube from inside in another operation. Before the extraction, we are going to cut at 5 different points, and we need to extract 4 parts, what we call the sleeves and the half tubes. And the difficult here, what is difficult here is that, as you can see, the half tube has a length of 2.7 meters, but the corridor where we intend to extract them is only 1.4 meters wide. So the first question is, can we extract these tubes with the space that it's available here in the building? And the other one is that we are going to repeat this operation 864 times, because we are going to extract from one side. Here you have 216 tubes from one side, and we are going to repeat it on the other side. And when you collect this, knowing that we are going to extract sleeves and half tubes, it's something that we would like to automatize. And the first feasibility studies we estimated 1 year for this operation, and it's in the critical path. So we wanted to explore other solutions to shorten this period, this duration. And that's why we called for the robotic expertise of the Jules Verne Institute of Technology located here in France at Nantes to explore if it's possible to design a robot for this kind of operation. So during this project, we worked together between EDF, the Institute of Technology Jules Verne, and also Graphitech in support to demonstrate that, yes, it is possible to extract these tubes in this available space, but we need to find a sequence of extraction of every tube because the environment is very constrained. And that was one of the results. Here you can see 12 different trajectories that we found for the tubes. That was another result, is that we don't need a specific trajectory for every tube. We can have only 12 trajectories that we can repeat for different tubes. So when we are going to deploy the operation, the operator is not going to think which of the 216 trajectories I have to apply to every tube. And we also take some lessons or guidelines to design the effector, the end effector, because here we're gonna have two functions. The first one is cutting to separate the tube from the vessel, and the second one is gripping, so take the tube and take it to the waste basket, or yes, basket. Here we also could make some feasibility studies and demonstrations in reduced scale mock-ups. Here is at the Jules Verne Institute of Technology, using a reduced model of the real robot that we intend to deploy in the nuclear power plant. But here you can see that it's really complicated to do it. Imagine doing this until operation. The movements that we found for the trajectories to extract the tube are really complicated. And here we realized that even if we were imagining to do it until operation, it was going to be very complicated. So it encouraged us to continue exploring this automatization of extraction, to continue developing the robot. And the next step was going with Graphitech to deploy the final solution. And here I'm gonna let Soulaimane continue with the presentation about the developments that we are doing right now in the choosing the final arm, robotic arm, and also in the design of this end effector for cutting and grasping.
Thank you, Juan. So let's talk about, let's go in detail now on the design and the implementation of the final solution. So just previously, some guiding design principle that we had on this project. The solution should be a semi-autonomous robotic system. The control room, it's controlled by a human, but outside of the building. That was another concern. And no human intervention inside the block reactor. That means we need to think about all the robot fallback to manage all the failure mode that we can face during operation. As Juan mentioned before, here is our scenario. We'll start by removing all the half sleeves, what we call half sleeves, little pieces in the first plate of the reactor. That can allow us to reach all the half tubes that also are stuck with the reactor. And we have to do that for each side of the reactor. So that means, I think Juan already said it, but we have a key figure here, which is quite impressive. We have the 864 times quite the same operation. So that gives us to guide us to something quite autonomous, to be more efficient during operation, and to allow the workers not to have a high load, cognitive load on their shoulder. So when we handle the project, we start thinking how to do it on a smart manner. So we say that there is some technical point that are missing till when we take the project, such as the cutting process or the gripping tools. So the idea was to start from those points to unlock those barriers and to launch what we call a trials campaign to validate those choices, and after that finish the design of all the solution in order to validate the overall system in one scale, full scale mock-up. Sorry. And for that, we also carry out some support analysis, such as risk analysis, FMEA. We assess also the dosimetry that the system will receive in order to see if it's acceptable for them to stay. And we chose also on some part of the system maintenance strategy. Not to be to shield all the parts, but maybe to replace them once or twice during the operation. After, so for the first point that we face is to define a cutting process able to remove the pieces from the vessel. So first of all, there were some circular shape of the cutting, and when we take the project, we say maybe we can change the shape. We can change to a square one. It allows us to have more space to remove the tubes. And also, it's easier to manage a robot for square shape, cutting square shape. So the pieces that we have to remove, it's stainless steel with a thickness of 35 millimeters, so something quite thick. And we have also some constraint, dimensional constraint. Because there is the sleeves are already stuck with the reactor that can't be removed. So we analyzed all the cutting process available on the market, and for our case, there were no cutting process on the shelf. So we decided to. We had a constraint. It should be a thermal cutting. So we have either plasma or laser, or so there are others also. But for plasma, there were no available cutting tools able to go through our sleeves. So we decided to go on laser to be able to have, even for laser cutting process, there were no on-shelf tools, on-shelf held, laser held, able to manage those cutting because of the design of classic laser head, I will say. So we, with some institute, we work to change the focal point of the laser head in order to have a focal point quite high, far from the head. So the idea was to keep the head of the laser, the head of the laser outside of the structure, and to have the focal point directly on the pieces that we have to cut. So we had some trials with the IREPA Laser Institute to validate this concept. And after that, we purchased a laser head able to have this characteristic. So here is a picture of the reactor from the top. We like Juan said, the robot will go through a corridor, and the idea is to design a gripper, something able to grip the pieces, but in the quite very constrained environment. So we propose to EDF to reduce some of the length, some of tubes, in order to reduce the constraint on the end effector that we design, and that was accepted by EDF. And we could design an end effector able to grip all the tubes in all the configuration, even the first one, the first one that you can imagine were the most constrained. So here is a picture of our hand effector, the final design, I will say. Multifunction, I'll put it in this effector, but two main functions are available. The first one is the gripping. We need to grip pieces, but we need to cut in the same time. So in the same tool, we have the cutting process and also the gripping process. And we'll show you after that the design. We also put, that was a key result from a previous study with Institute Technology of Jules Verne. We use visual control, sorry. We use visual control in order to replace the real robot from its model position to the real position. And it's quite, with a camera, we can adjust the position of the robot of what we had to remove. So here it's a model of an effector simplified one. But just to show you the philosophy, first we will use all the robot movement to make all the cuts, -1. The idea is to grip in the same time when we cut, not to release the pieces in the reactor. So we let one cut that will be managed by the movement directly inside the end effector. And you can see there is the last one, and we can release the pieces that we have to retrieve. And after that, we design all the overhaul robot, and it's a video of the trajectory, the remove trajectory of the tube. Just to some key figures also, we assess the flow, the operation, the time of the operation, and for that like Juan said, we were at 1 year operation, and we reduced the operation to 5 months only, including maintenance. And that's quite a good result for this project. Where we are now, so we purchase all the tools of the equipment to carry out, to manage the first campaign, which will be cutting trials directly inside our demonstrator, our industrial demonstrator near Chinon power plant. So we had the robot. We purchased also the end effector here, the mock-up to be used on this campaign, and we will carry out those trials beginning of 2026. Hope. A quick video of the operation that will be on this campaign, the cutting campaign. So like I show you, there is first some cuts done by the movement of the robot. And at the end, when the end effector will be inside the piece that we have to retrieve, there will be a last cut done by a movement directly inside the end effector. Allow us to remove the piece. So next steps is to finish the overhaul design of the robot, meaning the carrier, the managing all the umbilical cable, and at the end we will perform integral trials on a full mock-up, full-scale mock-up, part of the reactor. But it's a full scale. Also in our industrial demonstrator. That is. So just to conclude, giving the constraints that we had on this project regarding the width of the corridor, the length of the tubes that we had to retrieve, we with the choice on technical bricks that we put on this project, we are now able to reduce the cognitive load on the operator to have something semi-autonomous, we'll say, not fully autonomous, and we reduce also the duration of the project, and that's a good result for us also. Thank you. Juan, if you want to say.
And just for the last word, is also illustrates the commitment at EDF Group for developing innovative solutions to improve our performance and keeping our time lapse in time. Thank you. If you have any questions, we invite you to discuss in the room. We will be there to answer if we can.
Thank you, everyone.
Thank you.
Thank you.